Okay, so we're going to continue our lecture on 6.5. Exponential growth and decay. Last time we derived the equation for a quantity that grows exponentially based on its differential equation. So we know that, let's focus on growth for a bit. Exponential growth. So there's something called a differential equation, which is just an equation with derivatives in it. And this was basically how a quantity that expands this way is defined, right? Its rate of growth is proportional to its current size, right? And we actually used, when you take differential equations, you'll learn that method called separation of variables. That's what we actually did, and eventually we did that and we solved it to look like this guy, PE to the RT. Now, a common question to ask about an exponentially growing quantity is how fast it is to reach some amount of size times its original amount. Often double. How fast will it take to double? So I actually put a formula in there to double. Time to double, or doubling time. Right? So if you start out with some amount P naught, how long does it take you to have double that is often an important question. How do you think we could actually figure that out? We have these two equations. So P gives us the current amount of the quantity that we care about. P naught is the initial amount, E is the exponential number, R is the rate of growth, which is often expressed as a decimal, which represents a percentage that it's growing per unit time, and T is time. Yeah?
You can divide both sides by P naught and then say that the ratio of P to P naught is 1/2.
Sure. Or you can just set P equals 2 times P naught, right? So to double it, right? So this means you have 2 P naught is equal to P naught E to the RT. You can divide both sides by P naught. And so this becomes ln of 2 is equal to RT, or in other words, T, which I put a little subscript D to emphasize it's the doubling time, is going to be ln 2 over R. So that's how you do it. You just pretty much plug in what quantity you want, and you can derive anything from these two equations. By the way, I don't remember if I mentioned this. I think it's on the paper. But the statement that says P at time 0 is P naught, that statement is called an initial condition. Right, so you really need to know what these equations are called, because sometimes you will be specifically asked for them. So this is called the differential equation. This is called the equation that gives the current amount. An equation like this is called an initial condition, and this is called the doubling time. By the way, there's nothing special about this equation, the doubling time. It's just that doubling is often something that's required. But you could see that you could have done the same thing for, like, how long will it take to triple in size, or how long it will take to quadruple in size. You just change the number here, right? So the time it would take to triple in size will be ln 3 over r. Time to quadruple in size is ln 4 over r, etc. Right? So if you want to figure out how long will it take to have k times its original value, it will be ln k over r. Okay? But doubling time is a very common thing to ask for, so they often ask for that. Now, when we're looking at exponential decay, it's a similar idea. It's something that decays at a rate proportional to its current size. So that means our quantity, its rate of growth looks like a negative rate, right? Because remember, when our slope is negative, that means it's decreasing. R is always considered to be positive here. It tells you the percentage change. But if you make the rate of growth negative, it will now decrease. And you can go through the same, exactly the same process that I did to solve this one, and you end up with P is equal to P naught e to the minus RT. And because this is decreasing, something that is often asked, again, is kind of the inverse of a double. How long will it take to have half of what you started with? This is actually called the half-life. This shows up a lot in, for example, chemistry. It often describes how something decays in terms of its half-life. Right? So that's half-life. This is the time taken to have half of what you started with. So if you have something that's decreasing, let's say you have 10 pounds of this thing, how long will it take before you have 5 pounds of that thing? Right? So that idea is called the half-life. And it also has a very similar equation to this, but it doesn't have any negatives in it, so I think I'll again show that to you so you can see how that's derived. So let's say we're deriving half-life. And so for this we'll set the current amount to be half of the amount that you start with. So this would mean 1/2 P naught is equal to P naught e to the minus RT. You can divide both sides by P naught. You can then ln both sides. And so you can solve for t. T would be minus ln of 1/2 over r. Now in the notes I gave you, it said ln 2 over r. What's the discrepancy? Is there a discrepancy? Yeah?
The natural log of 2 is equal to the negative natural log of 1/2.
Right. And how do you know that? By the log rules, ln of 1/2 would be what?
E.
Yeah?
ln1 minus ln2.
ln1 minus ln2, right? There's the thing that says the log of a division is actually a subtraction of logs. What's ln1?
0.
That's 0. And so you have minus times a minus, that gives you ln2 over r. And for emphasis, I'd like write that with t with a subscript h. This is called the half-life. So if you know how fast something is decreasing, you can figure out how, and you know it's decreasing exponentially, you can figure out how long it will take to have half of the original substance. And in this sense, you can actually backdate when it would have had a certain other amount of substance. And so that's how often you would date things radioactively, once you figure out their half-life. And so, for example, let's say we can say, okay, I have a quantity that's radioactive, and it's decreasing by, it loses 30% of its mass every month. It's super radioactive, right? Then I would just simply plug in R equals 0.3, right? And so to figure out its half-life, it's just ln2 divided by 0.3. So that's an example. Okay. And I'm pretty sure you were convinced of this maybe back in Calc 1 or so, but I don't need to convince you, hopefully, how applicable something like this is. Exponential functions show up in nature all the time. I showed you that how E arose from taking this compound interest idea, and exponential growth and decay and all that stuff, it's used all over the place. You'll see it in almost all of the sciences, right? You'll see it in engineering, in biology, in chemistry, in financial mathematics, in mathematics. Like, it's all over the place. So I know you guys saw a lot of examples of that, but we're actually going to move on. Let's actually do a couple examples, then I'll talk about another idea, and then we'll do some more examples. So let's do examples 1 and 2 based on what we know so far. One of the reasons why I gave this is because I didn't want to write all this down. So this is examples. Note that they're from the handout. And it's posted on the website, the same place where you can find the answers to the quizzes and stuff. Right. So in an exam or a quiz or a test, if I ask you a question under this topic, it will be a word problem, so just so you know, it will look like this. Probably not that many parts depending on how long the test is, but this is a typical way that you'll see a question asked. So let's see it. So let P of t be the current size of a population of a colony of bacteria at time t. At 10 a.m. there are 50 bacteria. At 3 p.m. there are 350. They reproduce very fast. Assuming the rate of growth of the population is proportional to its current size, that sentence is what tells you that you should be doing exponential growth. Right? So there's something different from linear growth, for example, but we have exponential growth. So that sentence is what tells you that we should expect exponential growth. So maybe I should write that down. Rate of growth proportional to current size. That sentence is what tells us that we're looking at exponential growth. And that tells us that the formulas in the first set of boxes are the ones that apply to this quantity. So that's what it tells us. Okay, now move on. So now we're given the size of the population at 2 different times, and we're told that we should expect exponential growth. And now it says find the relative growth rate of the population. So A. What is the relative growth rate? What symbol is that in our equations? Yeah?
Is it R?
That's the R. So in part A, we're asked to find the R. Okay? Ideas, finding the R. Yeah?
Set up the exponential growth equation and plug in what we know.
Okay. So we know P would be P naught e to the RT. How do we know that? Because we're told that it grows proportional to its current size. It exhibits exponential growth, therefore this equation will govern its current size. We also know at 10 a.m., which from henceforth shall be denoted as time equals 0, right? That's the first part, time we're told about where this population is. So I'll assume that's the initial time. We know that P of 0 equals 50, right? This is also, by the way, P naught. Also, at 3 p.m., this here is when time is equal to, well, we know that P of 3. What is time equal here?
5.
Hmm?
5.
So let's say we're measuring in hours, right? Because they're giving us by clock. So we're going to measure in hours. It's going to be 5. I know that P of 5 is equal to 350. All right, so these are 2 pieces of information we're given. And we know that equation. So we know that we have 50 is equal to P0. We also know that 350 is equal to P0 e to the r times 5. So you have these 2 pieces of information. What we can do is simply just plug the first equation into the second one. So we have 350 is equal to 50 e to the 5r, and now we solve this using our logarithms. So we divide by 10, 35 divided by 5, that's 7 is equal to e to the 5r. This would mean that our r would be ln of 7 divided by 5. And I'd accept an answer like that. You don't have to actually give me an approximation. But if you're curious, and anyone has a calculator, you can tell me what that is roughly.
.3892.
0.38,
Yeah, 92.
0.3892, blah, blah, blah.
Yeah.
Right, so here in this population is growing very fast. It's growing pretty much by almost 40% every hour. That's very fast. Some serious bacteria. Okay. Now let's go on to B. Find a formula for P of t. P of t would be equal to what? Well, we know it's P naught e to the RT. E is E. T is the independent variable, so we're not going to change that. P is the dependent variable, so we're not going to change that. So when they ask us to identify the equation P of t, we need to fill in P naught and we need to fill in R. We just found R, and so this means that our P would be P naught, which is 50, e to the ln 7 over 5 times t. And that would be the answer to B. What is the size of the population at 4 p.m.? How do you find that?
Plug in 6 for T.
So here, t equals 6, because we started at 0 to be 10 a.m., so this is 6, and we want p of 6. So this simply means you plug in 6 for t. And that's the answer. D. What is the rate of growth at 4 p.m.?
3892.
Yes, I know the phrases are kind of similar, but they're actually different. Relative growth rate and rate of growth are very different. Relative growth rate refers to R. When I talk about rate of growth, I mean the rate of change of P overall. In other words, when you see the phrase rate of growth, it's talking about P prime. So rate of growth here actually means P prime. All right, you'll use the word relative or the growth constant if you want to refer to the R. It's a matter of convention. So how would we find P prime when we're at 4 p.m.? Do we have an equation that has P prime in it? Right, we know that P prime of t is equal to R times P of t. So this means P prime at time equals 6 is just R times P at time equals 6. I actually know what R is. Let's just put actually ln 7 over 5 times P of 6. I just found that 50e to the ln of 7 over 5 times 6. The thing is, once you have all these equations, the actually answering the problems, they're not that bad. Okay. So let's make a prediction here. If the population keeps growing the way it is, when will we have 1,500 bacteria? Say when? Yes, not what. When. And of course, when means we want a time. Okay, so what do you want to do here?
So 15,000 equal, or 1,500
Yeah.
equal to 50E.
Right, so we know this is true, and so we know that 1500 is what we want the current size to be. It starts off with 50, e to the ln of 7 over 5 times t, and we want to find that t. So we can divide by that. 150 divided by 5 is what, 30?
Yeah.
Is equal to e to the ln of 7 over 5 times t. So this means that we have ln of 30 is equal to ln of 7 over 5 times t. This implies our t is equal to 5 ln 30 divided by ln of 7. What is that roughly? Calculate. I'm okay with you writing the answer and leaving it like this.
8.7393.
8.7393, and this is in hours after Kenya. Questions? As you probably noticed, the hardest part of these problems is actually deriving the general formula. But once you have that general formula, everything else is kind of straightforward. But anyway, let's move on to problem 2. The half-life of a radioactive substance is 30 years, right? This means after 30 years you will have half of what you started with. Suppose we have a 200 milligram sample of the substance and let P of T be the mass remaining after T years. Okay. So 1, the tip-off here is radioactive substance. This makes you assume exponential decay. Radioactive substances decay exponentially. And we're given the half-life. We know the half-life is 30 years. So we're going to time in years here. Okay. Find the differential equation satisfied by this quantity, P of T. So when it says differential equation, what's it referring to?
P prime equals R.
P prime equals RT, RP minus, right, because it's decaying. So basically here, we basically need to find the R. How do we find R?
The half-life equation?
The half-life equation, right? We know that TH is equal to ln2 over R. This would mean that if I know the half-life is 30, this is equal to ln2 over the R. This means that R is equal to ln2 divided by 30. And this means, therefore, that P prime is equal to ln2 over 30 minus times P. That's our answer. B. Find a formula for P of T. Well, we know that P is equal to P naught e to the minus r of t. This means that P is equal to P naught. Do we know what that is? Yes, 200. E to the minus R, we just found is ln 2 over 30 times T. So that's our formula. How much will remain after 75 years? So in part C, we want P of 75 basically. So this is going to be 200 e to the minus ln 2 over 30 times 75. And whatever that is. It's going to be 200 times some factor of 2. Factor. How long will it take to have 1 milligram? Well, again, we know that P is equal to P naught e to the minus RT. So I'll just plug in 1 milligram for this guy. And solve for the difference. 1 is equal to P naught, which is 200 e to the minus ln 2 over 30 times T. This means that 1 over 200 is equal to e to the minus ln 2 over 30 times T. This means ln of 1 over 200 is equal to minus ln 2 over 30 times T. This means that our T is equal to minus 30 times ln of 1 over 200 over ln 2. ln of 1 over 200, using a similar argument for ln of 1/2, this just becomes positive ln of 200 over ln of 2. Here. E, what is the rate of growth at this point? Well, we know that P prime is equal to minus RP, so that's equal to minus ln 2 over 30 times time. What is the rate of growth at the time where there's 1 milligram remaining? So here we'll plug it into that guy. So it's going to be 200 e to the minus ln 2 over 30. And then you plug in the time for there to be 1 milligram, which we found in the previous one. 30 ln of 200. Over ln of 2. Now that answer can be very much simplified, but at this point I don't really care about simplifying. Just want to know that you can understand the equations, know when to use them. Any questions on that? Yeah.
What is that you plug in for P? Because don't we just have 1 milligram, so that isn't P the amount that we have?
Oh yeah, that would actually simplify. I was just going straight by the formulas, but yes, that would simplify to 1 milligram.
Okay. So you could just do 1 R.
This is going to be, if you actually plug this in, yeah, that actually does simplify. Notice that this would cancel that. 30 here will cancel the 30 here. I have e to the minus ln of 200. It's actually just 1 over 200. So it's just minus ln 2 over 30. Or yes, you could just realize that this was minus r times p, And we knew that our current amount, P, is supposed to be 1. So in this case, it was just minus R.
Okay.
There's another important idea, and again, you'll explore this idea when you get to differential equations, as well as in other spheres. Maybe again in some chemistry class you'll talk about it. Newton's law of cooling, or Newton's cooling law. So Newton figured out this law about how fast things cool down. If you take a hot substance that's hotter than its environment and you put it in a cooler environment, how long will it take? How does its temperature change when it's in this new environment? This is called Newton's law of cooling, figuring out how fast objects cool down. And what he discovered is they actually cool down exponentially. Right? Like the hotter they are, the faster they'll cool down. And then as they get colder and colder, they lose their temperature slower and slower. And it's a law that he pretty much came up with empirically, right? So there's no like mathematical derivation of this law. It's something that he measured things, right? He timed things, he measured things, and he came up with this law. And he figured out that we have the rate of change of temperature is actually proportional to the difference between the current temperature and the ambient temperature. Right, so T is a function of T, where the big T represents temperature and your little t would represent time. So it's the temperature of some object, little t represents time in whatever units. And he figured out that the temperature change, how fast the temperature is changing, is actually based on the difference between the current temperature and the temperature of the surrounding. Right? So the closer the current temperature is to the temperature of the surrounding, the slower the temperature will change. And this actually happens exponentially. So if you're like super hot, you'll cool down super fast. But if you're only lukewarm, you'll get to room temperature actually a lot slower. It'll take you a longer time, you know, to get to room temperature if you're already almost at room temperature, relatively speaking, of course. Okay, so that's an empirical law that Newton figured out, and it's called Newton's law of cooling. And so we can, in the same way that this is called again a differential equation because it has derivatives in it. So it is something that you might study in differential equations class, and so. I'm pretty much going to solve using separation of variables again. So again, here we have basically d big T with respect to d little t is equal to k times b big T times t a and b. And by the way, t, a, and b is a constant. If a and b stands for ambient, stands for the surrounding temperature, right? T is actually the variable here, right? So this is a function of t. And that is a function of t, but this is a constant. K is also a constant, it's a constant of proportionality. And so what we can do is we can actually separate the big T's from the little t's. Right? This is why it's called separation of variables. I can take this entire thing here and divide by it. Right, so this means my object is actually different from the surrounding temperature. And so I can move the little t on this side. Remember, k is a constant. At this point, I can integrate both sides. What's the integral of this? 1 over t minus t.
Natural log of the absolute value.
Alright, technically you do a substitution, u equals this, but the du would be actually 1 dx. So it just becomes that. And so this guy becomes what? Kt plus a constant. Okay? And so now you want to solve for t, you can set this, raise both sides to the e. This side would of course be some constant times e to the kt. And this would be t minus ta and b. We don't have to worry about the signs here because I can just change the sign of c to account for any sign change. And usually we think of this in terms of a warmer object cooling down to T ambient, so this is normally considered to be positive anyway. But even if we wanted to generalize it, it's okay to not worry about the plus or minus here. And so now we know that the temperature of the object is going to be the surrounding temperature plus some constant times an exponential function. And this is the solutions to Newton's cooling law. So if you want to figure out or predict what the current temperature will be at some time, you can actually use this equation. Once you figure out the big C and the K. So in this one there are two unknowns here. Well, similar to the other one. Well, there are three if you come. Well, this would be known to you in theory, but these two unknowns you'd have to find. Kind of like your P naught and your R. So of course, if this object is hotter and it's cooling down, this is going to be decreasing. So that would be, the K would probably be negative. And if it's the other way around, it would be positive. That brings us to example 3. And we'll do example 3 and then end it. Thermometer is taken from a room where the temperature is 20 degrees Celsius to the outdoors where it's actually colder, it's 5 degrees Celsius. After 1 minute, the thermometer reads 12 degrees Celsius. What will the reading be after 1 more minute, and when will the thermometer read 6 degrees Celsius? So this is part A. So what information do we know? We know the original temperature of this object, right, being the thermometer, is 20. It's put into an environment where after 1 minute its temperature is 5. Well, its temperature is 12. So when time increases to 1, and I'm thinking of time in minutes, the temperature drops from 20 to the number 12. We also know here that the ambient temperature, that's the 5, right? It's 5 degrees outside. The object is 20 degrees, the outside is 5 degrees. After 1 minute, the object is 12 degrees. What will the reading be after 1 more minute? In other words, here, what we want is T of 2, given all this information. So since we know that T is equal to T A and B plus C E to KT, we have two of the following. We know that this guy is 20, that guy is 5, plus this is C E to the KT. Don't really know any more information here. Well, I do know that this happened, the 20 happens when T is 0, right? So that's E to the 0. I also know this one. The temperature is 12 when the time is 1. So this is 12 when that's 5 plus C E to the K times 1. That's the information I know from here. This means what? Well, we know that 20 is equal to 5 plus C, which means that our C would be 15. So we found the C. And so this would mean that 12 is equal to 5 plus 15 times e to the k. By plugging that guy here. So now it's 12 minus 5, that's 7 divided by 15 is equal to e to the k. And so we know that our k will actually be ln of 7 over 15. You can also notice that that's actually a negative, right? 7 over 15 is less than 1, and once, remember your log equation, 1 is here, so if you're less than 1, your log is actually negative. So that makes sense, and this guy is actually decreasing. So what do we have here? So this guy would be 5 plus c 15 e to the ln of 7 over 5, 15 times t. And so when t equals 2, our t is going to be 5 plus 15 e to the ln of 7 over 15 times 2. The idea being, as time goes on, this guy is going to eventually become 0, because the negative exponential decreases that way, and it will settle towards 5. So that's that. Needs to be. When will the thermometer reach 6 degrees? When will t equals 6? Well, we actually figured out a general formula for t. So this would mean 6 is equal to 5 plus 15 e to the ln of 7 over 15 times t. And I want to find the t. So this would mean that 1 is equal to 15 e to the ln of 7 over 15 times t. So this means 1 over 15 is equal to e to the ln of 7 over 15 times t. This means that ln of 1 over 15 is equal to ln of 7 over 15 times t. This means that t is equal to ln of 1 over 15 divided by ln of 7. You notice that this is a negative number, that's a negative number, negative divided by negative is positive, so it is some positive time in the future, which makes sense. And that's it. Any questions on these? I feel like once you know the general forms, it's not that bad. So it just comes down to memorizing the forms and knowing when to use them, what the buzzwords are to know to use what formula. We'll do one last example and then we'll finish this, and we'll actually start talking about trig. We're going to learn to do all sorts of nice integrals with trig, I think, is the next topic. We'll stop there. I have stuff to give back.